Thank you very much for the introduction. Good afternoon, everyone. So my name is Arno Ricou. I work at Quandela as a team lead in the applications team. And today I'm going to talk about the Quantum Toolbox. What is Quandela Quantum Toolbox? It's a set of easy-to-use, cutting-edge quantum algorithms that will enable to unlock tens of use cases. But before moving on to the Quantum Toolbox, I'd like to talk about the company Quandela at first. So Quandela's mission is to bring a useful quantum computer on the market, as well as enabling organizations to achieve their quantum transformation. Concretely, how do we do that? We start by building hardware. We build photonic quantum computers, so quantum computer based on particular light. This is called Mosaic. We also commercialize some component of our quantum computer to R&D labs like ED-Light and Prometheus. And we install them in data centers, HPC centers, research centers, and so on. And on top of that, we have Quandela Cloud. So Quandela Cloud enables any user that has access to the internet to actually compute on Quandela quantum computer. Today, you can use our 10-photon quantum computer, and next year you'll be able to use our 20-photon quantum computer on the cloud. And this will help us to upskill professionals as well as academics and developers. Then we have a strategy around hubs. So once we have a quantum computer with a quantum cloud around it, we are developing a hub, which is an ecosystem of partners with application like use case providers, like big corporates, as well as people knowing having the know-how, the expertise of each industry, as well as people having the skills in quantum algorithm, so that they work together in order to create value using this quantum computer. And then all of that is packaged into the Quandela, the quantum transformation, and we sell that through our quantum acceleration program, I will talk about in much detail in the following slides. And this is done across industries, so we're targeting any industry such as finance, energy finance, travel and transport, pharma, automotive, chemicals, and so on. Our quantum computer is data center ready, and it's a quantum computing system with a proven track record. So we delivered our first quantum computer to OVH Cloud. So it's a private data center located in France, in the north of France. And the delivery time was 8 months. That's really a record time in order to build and deliver a quantum computer. And the number of quantum operations per second is 144 for this device. Then we're able now to deliver 12-qubit machines, so 12 photons, with a delivery time of 12 months and a number of quantum operations per second of 576. And we are now currently working on the next version of Mosaic, our quantum computer, with 24 qubits, meaning 24 photons, and above 2,000 quantum operations per second. This is our cloud offering. So you have different offers according to your needs. So you can first explore Quandela Cloud with some free credits. So if now you're interested in trying out our quantum computer, please go on cloud.quandela.com, and we'll provide you with free credits so that you can have some runs on our quantum computers. Then there's an academic plan for people wanting to do research using our quantum computer, and a pro plan. This is the price per job, and then you will need to have some additional price for each number of shots. And then we have a tailored plan for enterprise. And for this, please contact us. You will have my email address at the end of the presentation. The quantum acceleration program is really important for us because, of course, it takes technology to achieve to create quantum value, but it's also it's necessary that people have the knowledge and the culture that is aligned with the quantum technology. And for that, we provide a quantum acceleration program because we think that it's not only a technological transformation, but also a people transformation. And this is going in few steps. First, the discover phase, where this is a phase where the client are understanding like the basic principle of quantum computing as well as the use case they may want to tackle. Then the design phase, when once we identify the use case, we're going to develop in a proof of concept some of these use cases. And then we'll do a scalability study to know when we're going to reach the quantum advantage for how many qubits, photon, what error level, and so on. Then we're going to put that in production in the deliver phase. And the end goal is the accelerate phase, meaning building a center of excellence where the company, our partner, are able to identify and develop their own use cases without our help. The title of the presentation was Quandela Quantum Toolbox. So there it is. It's a set of 5, for now, easy-to-use algorithms. So what we try to do in that is really package state-of-the-art photonic algorithm in order to make it easily accessible to our end users. So it's just plug and play for you. Like you, for instance, you want to compute the ground state energy of your molecule, you just have to type the molecule you're interested in. And then it runs the computation for you on our quantum computer, and it's fully optimized for that. We have 5 different algorithms doing so 3 variants of VQE. VQE chemistry in order to compute ground state of molecules. Here are few molecules we computed the ground state of on our QPU. VQE custom, where in this one the input is just a Hamiltonian, so it's a really flexible input, and you can use this toolbox in order to address like different kind of a problem that you manage to formulate into an energetic formulation. The CVAR VQE, which is more tailored to combinatorial optimization problem. And then 2 algorithms based on graph. The first one is the graph isomorphism problem, an algorithm which enables to, starting with 2 graphs, check if they're isomorphic, meaning if up to relabeling of their nodes, they're equivalent. And then the last one is the dense subgraph identification. And for each of these algorithms, there's use cases that you can unlock. For the first one, computing the ground state of molecule, the obvious one and the one most people go for using VQE is battery design. In order to, if you want to use like the custom VQE one, you can compute different, you can try to compute different ground state of molecules, but you can also use it to solve differential equations, for instance. I will come back on that later on. About CVAR VQE, we managed to use it to solve multi-agent pathfinding problem or even train unit assignment problem. Again, I will give more details in the following of the presentation. The graph isomorphism problem can be useful for fault detection on chip or even for cross-checking database in informatics. Last but not least, the dense subgraph identification can be central in molecular docking problem. Now let's go into a bit more details in each of the use cases I just mentioned. So for the VQE chemistry, where it's used to compute different ground state of molecule, you could use this one, and just as a reminder, the problem is to compute the ground state of large molecule. And this becomes largely and quickly infeasible classically as the computational size of each Hamiltonian is like growing exponentially with the number of molecules we have and the number of electrons that we try to represent. For that, we use quantum VQE, so like quantum computation and quantum molecular computation. And one way to use this algorithm in order to tackle larger molecule is what we call the DMET VQE. So it's it's a part of the active space method where, say you have a big molecule, let's say a molecule, H10 molecule, you can cut this molecule in different pieces of its 5 times H2 molecule, and then you compute the VQE on each of them, and then you put them back together. And this is key because you can do that using our easy-to-use algorithm and benefit from like our really accurate result and the accurate result of quantum computing for a larger molecule. The plot you can see on the right is iteration of the VQE algorithm on the H2 molecule running on our QPU. Another interesting way to use our quantum toolbox, and especially the custom VQE algorithm, is to solve differential equation. So we partnered with EDF, so the French electricity provider, on a use case which was about predicting how a crack in the dam is going to evolve with some constraint applied on this crack. This problem is usually solved with a finite element method, but we can have an energetic formulation of that problem that we fed into our custom VQE, and we managed to solve the problem. Moreover, we showed that with this algorithm, we have a scaling that is at most polylogarithmic in the resource of the problem. So it scales really efficiently. So that's another example on how to use one of our toolbox algorithms in order to develop a use case. CVAR VQE, as I told you, can be used for multi-agent pathfinding. So multi-agent pathfinding is really like present everywhere in logistics. It's about taking multiple agents and trying to, for all of them to find a path at the same time. This is a notorious NP-hard problem, thus of interest for quantum computing. Even though we know quantum computing won't solve any NP-hard problem, we hope that some heuristics will enable to increase the speed of obtaining a solution. We co-developed with the client the energetic formulation of that problem, and again, we feed it to our CVAR VQ algorithm. We was able to return the result. And we know as the QPU size will grow, that at some point we will be able to tackle this algorithm for large scale, like interesting scale for industry, and being more efficient than classical computers. Another way to use the CVAR algorithm is with a similar-ish problem, which is called the train unit assignment problem, which is something really known in railway transportation. And again, we used a similar algorithm. I won't go into the details for this one. And we show that it's specifically interesting because this quantum heuristic is like sample efficient. So you don't need a lot of shots of your quantum computer in order to run it, which is crucial because it means that you can run it fast, actually. And then it's resilient to noise. One illustrative algorithm, so this is an idea we had. We didn't have the chance to implement it yet, but that's something that's work in progress, is about comparing different databases of chemical information. So the bases you use in order to represent chemical information are really various. So the idea here is to try to represent each machine-readable component by a key, and then you compare those keys and try to make the basis behind modify a bit. And once the key corresponds to each other, then you will know what bases they have in common. And the way you compare those keys is using some graph isomorphism. And this can be done with a native algorithm on our photonic quantum computer. It's quite this algorithm is really interesting because it really exploits the hardness of boson sampling in order to solve like industry useful algorithm. Another useful algorithm for the family of graph algorithm, but this one is related to the dense subgraph identification, is about molecular docking. So this one has been addressed in this paper by Xanadu a few years back, where they did a mapping between Gaussian boson sampling and molecular docking. There's a similar mapping between boson sampling and molecular docking. Boson sampling is like a variant. Gaussian boson sampling is a variant of boson sampling. And the idea, roughly speaking, is like to take a molecule and a ligand and to try to represent in a matrix and in a graph all the different composition you can assort this ligand and protein together. And then by computing the dense subgraph in this big graph representing all the conformation of this protein and ligand, you will know which one is the more likely to happen, thus which one is going to happen in real life. And again, this is using some dense subgraph identification, which is native to our device, using like boson sampling, which is what our device is really good for. And we believe that when we scale up, we know that boson sampling has an advantage on classical. I mean, we cannot simulate boson sampling efficiently. We have an advantage over classical computers, so we believe it's a really good candidate to prove some quantum utility on the short term. If you have more questions about the quantum toolbox of algorithm, please visit our booth or try it yourself on cloud@quandela.com. If you have any questions, please feel free also to contact me either on my email address or on LinkedIn. Thanks for listening.
네, 고맙습니다. Q&A 잠시 진행하도록 하겠습니다. 혹시 질문 있으신 분께서는 거수해 주시면 마이크 전달해 드리도록 하겠습니다. So we are going to have a short Q&A session in case of questions. 자, 질문이 없으시다면 조금 전에 이 PPT 마지막 장에서 보신 것처럼 이 QR 또는 부스를 방문해 주시면 되겠습니다. Booth number S11, right? S11.
That's a really good question.
Yes.
Yeah, I think so.
Quandela
We're just around the corner there.
맞습니다.
So I'm told so you'll be able to see me if you pass by.
네, 키가 크셔서 아마 잘 이제 인지가 되는 우리 아르노 리쿠님 오늘 두 번째 발표 함께 해주셨는데요. S11번 방문하시면 콴델라 부스에서 더 깊이 있는 질문 편하게 하실 수 있겠습니다. 발표 진행해주신 아르노 리쿠님에게 다시 한번 큰 박수 부탁드리겠습니다.
Thank you very much.
Thank you.